Hi, a very good morning, good afternoon, and good evening to all the attendees for the virtual event for DSS Asia. This is our third virtual event, and I am really happy to see increased participations from all our friends around the world. We are starting to see increased adoption of distributed SQL to help address some of the biggest challenges in architecting for the cloud itself, as well as to address some of the current challenges in monolith databases. So we are very happy that you are joining us in this journey where our customers and some of our technology partners are sharing how they're leveraging distributed SQL and Yugabyte to address some of the common and biggest challenges in their digitization journey. Now I'll hand the stage over to Karthik, our CTO and our co-founder, and where he will kickstart the keynote for this event. Once again, thanks for joining me on this distributed SQL journey itself.
Hi, everybody. Welcome to our annual Distributed SQL Summit Asia. Extremely excited to have all of you folks here. We have a ton of excellent speakers, great knowledge sharing sessions. So let's kick it off. The keynote title for this year's DSS Asia is E Cubed, Embrace, Extend, and Evolve. Well, that refers to embracing, extending, and evolving PostgreSQL, but no good keynote in today's day and age is complete without a reference to ChatGPT. So the subtext is PostgreSQL meets Hello Bard. Let's look at what that means. Well, for those of you that know ChatGPT, Bard is Google's equivalent. ChatGPT servers were always full, so we could only get Bard to work. So, without further ado, let's just stick to Bard's version of the answers. Okay, so we said, since ChatGPT and AI knows everything, we asked ChatGPT, what is the fastest growing database in the world by usage? If you guessed PostgreSQL, you're right. So it is PostgreSQL, and it tells you a whole bunch of other stuff about it and who adopts it and so on. Okay, so why is this important? It's important because PostgreSQL in today's day and age is fast becoming the de facto database API. It's becoming the standard to build applications against. That's because it has powerful relational capabilities that match like other really powerful databases like Oracle, and very robust and mature. It's been hardened over many years. It's fully open source, permissible, extensible, etc. And there are a lot of large companies and cloud providers adopting it, backing it, and making it better, right? And not to mention, it's won a whole bunch of popular database. This developers love that, the database of the year for a bunch of years. So all good things. So the first thing in building Yugabyte DB is we thought, let us embrace PostgreSQL, right? Because it is so popular, it is becoming the standard. Now, what is Yugabyte DB? Yugabyte DB is a PostgreSQL compatible distributed SQL database, and you use it to build cloud-native transactional applications, right? For those of you wondering, what the hell does Yugabyte mean? Yuga in Sanskrit is an epoch or an eon, and byte refers to data. So this is data that lives forever without any limits, right? So the industry's preference is clear. They are embracing PostgreSQL. Everyone's embracing PostgreSQL. PostgreSQL is always in the news. Somebody's supporting it. Someone's doing something else to it, so on and so forth, just like what we're doing here at Yugabyte DB. Now, in all of this, it's important to think through what does PostgreSQL compatible mean, because there are a number of databases that say they're Postgres compatible, but there's different levels of compatibility. The lowest level of compatibility is just client driver compatibility, where you can use Postgres client drivers to interact with the database. One step up is the ability for the database to parse Postgres syntax and maybe ignore some pieces of it or execute other things differently. A step further is like feature compatibility, where there's an equivalent feature for a number of things. Like, for example, if you're thinking about triggers, you'll have something equivalent, but it's not exactly the way PostgreSQL triggers work, right? So in this case, you have to change your application. Developers have to relearn the syntax of how to use these features, but they do exist. And finally, there's runtime compatibility, where everything looks and behaves like Postgres. Now, it's important to realize that the last form of compatibility, runtime compatibility, is extremely critical in order for the database to behave just like Postgres. at Yugabyte DB, obviously, we adopted this level of compatibility so that Yugabyte DB appears and behaves just like PostgreSQL to all applications and to developers and to anybody using it and to DBAs and et cetera, et cetera. So how do we do this? Well, we have a query processing layer that is completely runtime compatible and the lower level storage layer, which is completely replicated and transactional and so on. And the most important thing is the only way we could achieve this is by reusing PostgreSQL code. Okay, so the first thing we did at a very, very high level is retain the upper half of PostgreSQL, the query processing layer, the parser, the analyzer, the rewriter, planner, executor, and start making changes to it to work against a distributed transactional substrate, right? And the second step is to figure out how we can make distributed execution even better in places where it needs to. If the data is all local, it starts to behave more or less like Postgres. If the data is distributed, it starts behaving completely distributed, right? Now, it's very, very important and cannot stress this enough from talking to enough users that the need for the database to be fully compatible with Postgres is paramount, right? It cannot just be kind of compatible. And that's because it instantly makes everybody familiar with this new database. They are instantly productive. They can port over existing applications, as well as they can have the guarantee that any of the ways their applications evolve in the future, this new database can handle it because Postgres could have handled it. Okay, so we talked about how we embraced PostgreSQL, how the whole industry, in fact, is embracing PostgreSQL. Let's get to E squared, the second step, which is extending PostgreSQL. Why do we need to extend PostgreSQL? Well, let's find out. So extending Postgres is to make it better. Now, you might say, how can you make Postgres better? Well, believe it or not, there are some limitations of Postgres, such as these. On the core database side, there are a few limitations. We're going to look at each of these in detail, but there's the dreaded transaction ID, XID wraparound issue, the vacuum issues related to vacuum, query planner hints that a lot of folks moving over from other databases like Oracle, SQL Server, DB2 really like and ask for. And other things like block level data compression, et cetera, et cetera. So there's a few things on the security side, like encryption at rest, password profiles. There's a number of things here that could extend the range of Postgres to be able to address even more. Now, here at Yugabyte DB, we really care about Postgres a lot. We are 100% open source as well. We'd love to work with the overall Postgres community to contribute as many of these things as makes sense upstream, but some of these are architectural in nature. So let's look at some of these, how we extend Postgres. Let's look at some of them in a little bit of detail. Well, the first thing is the transaction ID, XID wraparound issue. For those of you that are familiar with the issue or not, well, PostgreSQL uses a 32-bit integer, a number, to assign to transaction IDs. So every time you perform a transaction, you get a 32-bit number and it keeps incrementing. Well, what happens if all of these numbers exhaust? Well, it turns out that while 32-bit transactions are large, they're not that large, and it is actually possible for a very busy set of applications running for enough time to exhaust this, and the database freezes after that. And this is something that we specifically had in mind when architecting Yugabyte DB. And we get over this by using a hybrid logical clock, which is actually time value, right? It's 64-bit. It's so big that it rarely gets exhausted. And it substitutes as the transaction ID and will never exhaust because it's more in tune with time, with the actual time that we keep on computers. Okay, the second issue we talked about was vacuum. And people who have worked with Postgres know that this is also another feared and dreaded issue, which is when the vacuum garbage cleanup, like when you make a lot of updates, the old original versions of those values that have been updated, they are no longer valid and they have to get cleaned up. And the process of cleaning this up is called vacuuming, right? And PostgreSQL copies and rewrites the whole row, called the tuple in Postgres speak, on the updates, and thereby leaving a bunch of unused rows or the old versions of the rows, which lead to table bloat and require vacuum, and then causes issues with your foreground applications. Now with Yugabyte DB, we were careful to pick a completely different storage model for Yugabyte DB. It uses what is called an LSM, or a log structured merge tree type of storage engine, and therefore it only writes updates and it compacts them in the background, and thereby it completely eliminates the vacuum issue. An additional benefit of doing the LSM-based storage architecture is that it is completely optimized for SSDs, right, which are becoming stock for transactional applications. And this is because SSDs also do log-structured file systems. And when you put a log-structured merge tree database on top of a log-structured file system SSD, it actually works really efficiently, and it keeps up the lifetime of the SSD for far longer than if you did a B-tree-based random write, which is what Postgres does. So in short, LSM is great for SSDs and great to remove vacuuming. Okay, the other thing we talked about is, there is a place for query planner hints. The way Postgres behaves by default is Postgres attempts to find out the best query plan, right? Which is when you try to execute a query, there could be a number of ways you could fetch and join and merge data in order to serve the result. And some of those ways tend to be far more efficient in terms of performance than others. Now, Postgres typically is really good at finding the best outcome, like the best way to munch this data. But a lot of users want to lock down the way this happens after you have figured out the best way, because you don't want this changing underneath you as your table gets more updates, et cetera, et cetera. So in these cases, a query planner hint becomes super critical. And Postgres has not really embraced this. There are some extensions out there, and there are a number of extensions for a bunch of other things. But Yugabyte DB, we took this, we put it into the database, we made this default, and we are extending it to increase whatever it can do, like extend its range of whatever it can address. So make it simple, make it more functional. Another example is, when Postgres stores data, there's no block level data compression. So your blocks are laid out uncompressed. And when you have a lot of data, this starts, and when you're thinking about data density and scalability of how much data you can fit onto a machine, this starts to become a problem. Now with Yugabyte DB, what Yugabyte DB does, it does two types of compression. The first one is row prefix encoding, where it keeps the common prefixes of every row. And the second one is compresses the blocks using a configurable compression scheme, like you could use Snappy, LZO, gzip, et cetera, et cetera. So this gives you you can trade off how much you want to compress versus how much CPU to decompress. And depending on the data set and the usage pattern, you can actually get the whole thing to work the way you want. So now you're going to be saying, okay, those are some issues. Yes, those are some big issues. But what about these other really big issues? Well, Postgres connections are slower. They take a while to establish and are hard to scale because Postgres actually spawns a process in the background every time a new connection is established. There's no pooling built into Postgres, connection pooling. Downtime, zero downtime upgrades. You have to frequently perform software upgrades, security patch, all of this stuff. How do you do that with Postgres without incurring a downtime on the application? It's either it's extremely complex setup, or it usually incurs downtime. And what about active-active setup to get high availability inside a single region? Because in the cloud and in cloud-native deployments, failures are pretty common. How do you deal with them? Well, all of these are legitimate issues, but they're not quite core to the database, right? And they require not just embracing and extending Postgres, they actually require evolving the PostgreSQL architecture. So let's find out the third leg of the journey, E-cubed, evolving PostgreSQL to distributed SQL. Let's jump right in. So in this evolving PostgreSQL to distributed SQL, well, the primary purpose is to be able to make PostgreSQL cloud native. Well, how do you do it? Well, the best way is, ask AI, ask ChatGPT, ask Bard. Well, so we did. We asked Bard, how can you make PostgreSQL really cloud native? And let's see what Bard said. Well, it was actually pretty good on a couple of points. It said, improve support for automatic scaling and self-healing, and simplify the deployment and management. And then it said something about improve integration with cloud services that had us going, huh? But well, if you guys know what that is about, do let us know. We always love to hear how PostgreSQL can be improved. But well, we said, let's go with the first two, right? And so here are the key points. Well, the first one was scalability. Second one was self-healing or availability in a single region. The third one that, probably ChatGPT didn't know about is geographic distribution of data. The cloud exists in many regions across many continents. So it's important to be able to distribute data across all of these regions. And the fourth one is about simplifying how you build applications with cloud native architectures. So let's take a look at all of these one after the other. All right. Up first is scalability. Okay, what is scalability? Well, your workload changes with time. It starts small, it grows big, and then comes medium, and then grows really big. It keeps changing over time. So it's important for the application servers as well as the database to be able to scale. And here we're going to take a look at the database side of things. Yugabyte DB is purpose designed architecturally to be able to scale horizontally, right? It can scale vertically too, and we'll come to that, but we're going to focus on horizontal scalability, which is really, really powerful as a feature for cloud native applications. Why is that? Well, let's say you have 3 nodes of 16 cores, right? That's 48 cores in total. Now, if your workload increased a little bit and you wanted to go from 48 cores to 64 cores, you can. The largest node available on the cloud is like, 96 cores or, something in that range. What happens if your workload actually exceeds that? Well, it's a 7-node, 16-core cluster, which isn't too big. So with Yugabyte DB, you can do all of these things. And that is built on a foundation of sharding data. So the way to scale is only if you can take your data and spread it across multiple nodes while still maintaining referential integrity, transactionality, all of that stuff. So each table can get split into smaller units called tablets. Each tablet is literally a group of rows, and all the tablets together form the entire table. And this is fully transparent to the end user. And you can have controls to say, do you want to randomly distribute your rows across the different nodes, or do you want to still maintain lexicographic sorting? So you have full control. You have the full range of functionality. You can prevent hotspots if you want. You can retain range queries if you want, while still continuing to shard. All right. So the second step after the table has been split is to distribute these shards or tablets across different nodes. And that's what it shows in the first part, the left portion of the diagram there, where the shards are distributed across 3 nodes. Now, in reality, you could have hundreds of shards per node, and so the cluster would operate totally fine. And if you wanted to scale, this can be quite easily accomplished by moving some of these shards to newly added nodes, like it shows in the diagram on the right. We just scaled a 3-node cluster living across 3 zones to a 9-node cluster, 3 nodes in every zone. So we have tripled the capacity per zone and made it and tripled the overall capacity of the cluster by making the CPU, the memory, the disk IOPS, everything pooled across these nodes, and so that the cluster behaves as a single Postgres unit. Now, the Yugabyte DB is internally smart enough to know how to rebalance data onto these new nodes and to do that very gracefully and to tell you when it started the rebalancing and when did the rebalance finish. So it's just is able to do the end-to-end operation, and it can do the inverse as well. A lot of people talk about scaling out, but scaling back in is equally important because sometimes your peak traffic goes away. Like for example, in the retail industry, October through January is the peak season, but after that, the traffic is not as high as it would be in the peak season, in the holiday season where everyone's buying stuff. So it's important to go both ways, and Yugabyte DB is built precisely to do that. Okay, so you're able to scale. Now, why is this important? Why is it important to be able to do scaling of any kind for cloud native applications? Well, that's because your needs of your applications are often unpredictable in themselves. I mean, let's say you have these 8 applications, right? You're the portfolio owner of these 8 applications or microservices, and they do something. And you've done a lot of analysis. Your team did a lot of analysis, and they said, we expect applications 1 and 2 to have quite a bit of growth, and the other applications, well, they're probably going to remain the same. But the reality is often quite different. Well, that was the plan, but in reality, application 1 never scaled as much as we expected it to. Applications 2 scaled a lot more than it did. But guess what? Applications 4 and 7 scaled a heck of a lot more than expected. And now it is scramble time, right? It's like press the red button, everybody get out there, make this workload work somehow, fire drill, et cetera, et cetera. This makes it very, very difficult and unpredictable. And, like I, myself, my co-founders, a lot of people at Yugabyte DB, we've been part of these fire drills. And what really happens is for 3 to 6 months or more, you don't have any work being done other than to scale your application to be able to meet the demand. And this is on the infrastructure side, on the application side, on the DevOps side, every side is focused only on this, and that just kills productivity, right? And it's a lot of tiring work that has to happen in order to accommodate unpredicted growth. It's a good thing, but it results in a not so good thing for the team. Now, all of this pain can be made a lot simpler by embracing cloud native architecture. You get seamless scalability, no need to compromise on SQL, and you do it. And the most important thing, right? Like people talk about horizontal scaling, vertical scaling. Well, it doesn't really matter how you scale. Horizontal or vertical is really a question of what type of machines do you want and how many, what units do you want to scale by, and so on and so forth. But the operation of scaling has to be simple, whether it's scaling out or scaling in. And the application should not get impacted. It should have zero downtime. And that's precisely what Yugabyte DB is built to do. So you may ask, okay, all this talk about scalability, but how much do you really need? Well, here's an example of a single application on Yugabyte DB, right? This is one of the largest automotive manufacturers in North America. And they are doing on a single Yugabyte DB cluster over 2 million transactions per second, right? And it's a 100 plus, it's almost a 300 plus terabyte data set, and it's still growing. And incidentally, we are approaching our first petabyte scale cluster, so multi-petabyte cluster that's going to go production pretty soon. So that's another data point for you. And this one cluster was a pretty big, reasonably big cluster. It had over 2,000 CPUs, vCPUs, right, across all these machines pooled in order to work in tandem in order to support this workload. So this is obviously an example of a pretty large application, but there are a number of reasonable sized applications out there in the world, even from small companies at this point, at this day and age. So let's look at the next cloud native property that we need to give PostgreSQL to make it really cloud native. It's availability. Right. And let's define it a little bit, right? For our purposes here, we're talking about availability inside a single region or a single data center. So just that, right? And so we all know that in the cloud native architecture, we use cloud native components or commodity hardware, and these things fail. So in cloud native architectures, failure is the norm. So when something fails, how do you ensure that your end application does not see the failure of the database, but the database still keeps working? So that's really what availability is about. Okay. So let's think about how would we do this with a Postgres or an Oracle or any traditional database. Well, you take a primary of this database and you would replicate it, do some form of logical replication, and you'd put up standby on the other side, right? And so now it does asynchronous replication, and you can make it kind of work like sync if you really want, right? There's different ways of doing that, but it comes with some trade-offs. Okay, so the primary is in one zone. Your secondary or your standby is a different zone. In this case, zone A and zone B. But when you lose a node or a zone, how do you automate the failover? Well, to do that, you really need an observer or a witness. So you need a separate service sitting in a different zone, because you don't want it to be a part of the zone that failed, that actually does the look on the two sides and see, oh yeah, the primary has failed, let me promote it, or so on and so forth. But what is the problem with this kind of a setup? Well, for starters, it's asymmetric. What happens if you lose the zone with the observer? Well, you have to go figure out how you do the failover of the observer, et cetera, et cetera. So there's a little bit of complexity right there. If your zone C failed and you're not doing the failover, then your automatic failover, which is your HA, can get compromised. When a node fails, you pretty much have to rebuild all of the data, right? So that makes it a little bit complex as well. And this is difficult to generalize, right? Like we're talking about 3 zones and 2 replicas. So you can tolerate one zone failure, even though with difficulty, you can do that. Now it's pretty common to have a zone failure and a node failure, because zone failures could last for, say, 6 hours. And you could have a node fail in the 6 hours. So you have to be able to architect the same thing to be able to tolerate 2 failures, which is, believe it or not, quite common. So how would you do that? Well, this architecture makes it extremely difficult to extend to such a deployment. The other piece of this is that your application has to be very aware of this topology. The application needs to know where it can do reads and writes, which is on the primary, and the application can do stale reads on the standby or the replica. And if the failover happens, the application now needs to switch over to the new primary and do reads and writes there, and the stale reads in the other place, and so on and so forth. This requires, in the application architecture, actually segregating all your reads and writes. All your writes have to go to the primary, and your reads now go to, these have to be consistent reads that go to the primary, and the others can be stale reads that go to the secondary. And so your application architecture becomes aware of this deployment, right? Which is really painful. So how does Yugabyte DB solve this? Well, it's done with both leader election and data replication following the same consensus protocol. It uses a consensus protocol where you put a node of the database or multiple nodes in 3 different zones, zone A, zone B, zone C, and they automatically enter into a raft consensus protocol. And so that already makes it a symmetric setup. You can lose any zone, you're still fine. As long as you have more nodes, you can rebuild data on a node failure. On a zone failure, you have 2 other zones available. You can actually survive 2 faults by going to replication factor 5 and just doing this across 5 zones pretty easily, because it's now a raft consensus of 5 members in the raft ensemble. And your application can do reads and writes from anywhere. So you don't have to force your application to think about what are the stale reads I need to do, and what are the primary reads I need to do, and where do I need to do my writes? It doesn't matter. All you need to do is to be able to reach a live node. So this makes it extremely simple, transforms some of the thinking along the traditional architectures to something far, far more cloud native, right? And so this gives availability. And note that with the ability to survive the failure of any one node in this case, because your raft consensus takes over and has other 2 replicas that serve automatically, you can actually, for a planned maintenance, like if you're doing a software upgrade, do this 1 node at a time and take a node down, upgrade the software, security patch, AMI refresh, whatever it is you want, and bring it back up, and do that with every node. And voila, you actually have the whole rolling operation across the cluster without compromising the availability of your application at all. And you can do that again and again, and even with any number of clusters, and handle the number of applications that are being built. You can actually handle them quite easily. All right. So let's look at our next cloud native property that we want to infuse into Postgres, geo-distribution. So why is geo-distribution important? Well, there are many clouds out there, like AWS, Amazon AWS, Google's GCP, and Azure from Microsoft, and a bunch of others. And each of these cloud providers has hundreds of regions or data centers available to you across different continents in the world. So it just becomes important at some point to be able to move data across these different deployments. And there's a number of different reasons why people would want to do that, right? But let's look at why and what this is about and why. Well, the 3 primary use cases for geographically distributing data are, number 1, disaster recovery. What happens if one of my regions fails outright? I need, for purposes of continuing my business and being able to serve the users, for that data and that entire stack to be available in a different region. So it's important to have disaster recovery. The second one is if anyone's running a global application where people access the data from all over the world, they may want really low latency, because there's a well-known study that says that as your latency and your performance of your application degrades and your latency increases, your engagement from your end user decreases. And this often impacts in an adverse way, the business. So you could have your, the monetization coming out, your total revenue coming from this actually drop because it's too slow. Because how many of us have actually abandoned a shopping cart because it was too slow, or not looked at a site or read something because it just took too long to load? So, we are all collectively the users of such applications. So performance for global applications is super important, which really means move the data closer to where it'll get accessed by the end users. And so you can compute and crunch and respond very, very quickly. The third thing that's coming up is there's a lot of regulation in this world. For those who are not aware, almost every country, every continent, a lot of them, they have their own set of rules which try to protect, because we're becoming an increasingly digital economy across the world globally. So in order to protect that, the governments in these various countries have some stipulations that say, all the data for all the citizens or people living in that country have to be stored locally, right? Because if you store it in a different country, then the question of who has rights and access to that data, and is that considered a breach of privacy? And a number of these type of issues start coming up. So data compliance and data residency and compliance become super important, where the data has to be resident in that country, right? Okay, so let's take a look at these three in sequence. Well, the first one is architecting for disaster recovery. So as we said, disaster recovery is when one region fails outright. Now, the traditional way of doing disaster recovery deployments is to use asynchronous replication between regions. But in these traditional deployments, even for a local regional failure, like, for example, that's what we saw in the availability section in the previous section, even if you have a node fail, you would trigger disaster recovery, right? And that's a very expensive trigger for just a local failure. And that's becoming even more expensive because failures are relatively common in cloud-native applications. So when you're doing asynchronous replication, it's extremely important to be able to do multi-zone replication, to be able to handle failures inside a region, to keep that inside a region, make availability happen inside that region in a multi-zone deployment. And in order to do DR, where you can do asynchronous replication across, that's one possibility, right? The other thing that Yugabyte DB gives you is to go synchronous across regions. The two things have their slight trade-off in terms of consistency, availability of data, and latency. Like in the one on the left, you will compromise your RPO or your data consistency a little bit. And everyone understands that in the event of a complete outright disaster, it's okay to lose a few seconds of data, but you get your low latency reads and writes from everywhere. And in the case of in the deployment on the right, which is synchronous replication across regions, everything is automatic. You don't lose any data, but your latencies could be higher if you're accessing data from multiple places. But there are ways to work around that and make it better too. But anyways, Yugabyte DB gives you fundamental building blocks in order to be able to handle disaster recovery with both synchronous and asynchronous replication. And this is a point of quite a bit of pride for us, because we're the only solution or the only database that does both synchronous and asynchronous at the same time, simultaneously. All right, the second use case is, how do you achieve global applications that have low latency or high performance, right? So you could use asynchronous replication, as we talked about. So you will have two clusters with the data, becoming consistent over time. And you could read from either cluster and you could place them far apart, and your data can get accessed closer to the geographies, closer to where your users are. And in certain cases, you can actually do writes and have them bidirectionally write as well, right? And each of these architectures has different trade-offs, but nevertheless, you have your choice of write consistency, lower your write consistency and get extreme write and read latency, or you can throw up a whole bunch of read replicas across different regions, and these different regions that have read replicas, you can actually access the data locally, and you'll be able to read them really, really quickly. And so that gives you a trade-off of stale reads, but really quickly, and your writes can just go anywhere and it'll make its way back to the core cluster that's shown here in North America, right? On the second diagram below. So we said for disaster recovery and performance, you can use asynchronous replication. And for performance, you could also use read replicas depending on what it is that you're actually trying to achieve. Okay, so let's go to the third use case. We talked about, data residency and compliance, right? What does that mean? Well, if you take this picture, a lot of countries actually have laws which say that if I were to spend money in the US, like do some financial transactions and then travel to Europe and spend money in Europe, and then travel to India and spend money in India, well, the different places say that the data for those transactions have to reside in the countries that I spent the money in. So the Europe data has to live in Europe and the India data has to be preserved in India, yet it's just me, one person that's traveled across and spent money. Now, I may want to view my last, 100 transactions that I have done. What are the places I've spent money? And if it happens to be across 3 continents, so be it. But most of the time, I know I wouldn't travel as much, hopefully. And so my access can just be local to wherever I live. So this type of a pattern is super useful to implement using transparent geographic partitioning. So just partition the data and pin them to different geographies, and you can query from across all the partitions and collate data without having to change the application architecture significantly, right? So it gives you the velocity and the best of both worlds. So we talked about how compliance can use row-level geopartitioning quite a bit. So anyways, the takeaway here is that it's not one, but there are multiple, 4 in this case, completely different fundamental modes of replicating data across different regions. And with the traditional world, with the Postgres world, you only think about the second one, which is asynchronous replication. But there's a lot more to that rabbit hole, and there's a lot more that you can accomplish with cloud-native applications with geographic distribution of data. So now let's get to the next section, which is simplicity of building applications. This is my favorite section by far. But before we get into it, obviously it is what it says. It makes building applications simpler, right? We already talked about how transparent scalability is, can really make applications simple. We talked about how if you have high availability, right, and we are able to tolerate failures, you don't have to take the ability to read from a primary and from a replica and split all that into your apps, and that makes applications simpler as well, right? And we talked about how, for example, in a lot of the geographic distribution cases, you don't have to build that logic into the application. Like, for example, with geopartitioning, you can actually partition your data while keeping your app the same, right? It doesn't even have to be aware of this. So application simplicity has been a theme already that we have seen in all of the previous things. But this section is specifically dedicated to how can we make applications even more simple. Okay, so let's jump right in. So what does a traditional application architecture look like with PostgreSQL? Well, it looks approximately like this. You have your different applications. They use a SQL driver, and then they go and they use logical connections. They'll go hit a load balancer. The load balancer will route it most likely to a connection pool like a PG bouncer, and that's going to go to one or more PostgreSQL databases. And you'll have multiple of this stack, floating around, depending on the number of applications. Maybe you don't want 3 applications hitting the same PostgreSQL database or physical server. You might hit it 3. You might actually compose it with 3 different stacks. Now, what's the problem with this setup? Well, let's list them out. First, right, your application SQL driver uses a certain number of logical connections, and that actually matters how many logical connections that you need to use. And so you need to maintain that in the app. You need to configure that and maintain that in the app. Now, one step from there, your connection pool translates the logical connections to the physical database connections, and it really needs to be aware of the application. And we'll look at what that means. Now, you need to also take care of high availability of the connection pool. You're going to do it for the database anyway, but you now need to do it for the connection pool. Well, you have to do it for the load balancer as well, if you're in a private cloud. But in public clouds, a lot of the public cloud vendors actually do that for you. The connection pool is not scalable, so you have to figure out how you shard between connection pools, et cetera, et cetera. And you need to figure out how to authenticate the connection pool with the database, because the connection pool uses a separate authentication mechanism. So when your app tries to reach the database, your app has to authenticate with the connection pool. The connection pool uses a different authentication mechanism with the database. And all the security stuff comes in there to make sure, is this really a secure setup? Because you're using 2 different levels of security, right? And finally, when it comes to the database, well, it's maintained by the DBA, a completely different team. Each of this is maintained by a completely different team. And you need to know how many physical connections your database can support for your given application. So you have to be aware of the application, and you need to scale it up and down. And so you need to figure out, based on a particular load, do I need to scale up or scale down, or what do I have to do? And obviously, scaling up and down is a complex and manually and operationally intense process, as we talked about. Not to mention, if you hit the largest size of node available to you, well, then you cannot scale your physical connections beyond that point, and you need to figure out how to manually shard data. So with that background, let's look at one more thing before we jump into the solution. Well, firstly, the connection pool and security are the security of the connection pool and authentication is a subset of the security options available in PostgreSQL. So, for example, you may have configured your PostgreSQL with LDAP, but getting LDAP to work with a connection pool is really difficult, right? And similarly, you really need to know your application. So the person setting up the connection pool needs to know which mode to set it up in. And that means you get different things. Like, for example, do I want really fast connections, and is it used by ORMs, but I don't get, your transactions, like I cannot use and I limit my number of connections. So because I get one set of connections per session, or do I use the transaction pooling where I get more connections and more efficient, but I cannot use a bunch of features, or I use statement pooling, which has even more, restrictions when you do begin trans and do a whole bunch of statements and commit. So there's a whole bunch of complexity here, and your application may evolve from one type to another over time, making this even more difficult. So how do we improve this architecture? Well, if you look at this diagram, let me go back. So from this diagram, the only thing we've changed here is replaced PostgreSQL with Yugabyte DB. So it's distributed SQL, it's horizontally scalable, but how does it change? Well, the first thing is you can split your database connections across multiple nodes. So you can add more nodes and get more connections. And so that means you don't have to really worry too much about, what is the app need, and are you at the maximum? Do you have to scale up, scale down? You can simply add nodes and remove nodes based on your connection requirements. And the next thing we thought is, why do we need this connection pool, which is external? This makes it another pain. Like the notion of logical to physical connections makes it very hard. Authentication and security is very hard. So we are pushing down the entire connection pooling, like architecture, infrastructure down into the database. So you don't have to think about physical connections anymore. And the database will implement connection pooling, and your application simply uses logical connections. And the connection manager piece inside the database will actually start routing these connections. Note that this is a feature that's currently under development. It should be available pretty soon, but it's extremely exciting, right? And the connection manager, now being a part of the database, can natively authenticate. Okay, we said, why don't we go a step further? Can we simplify this even more? And we said, why don't we just try to eliminate the load balancer? It's just an unnecessary thing that everybody has to set up. And as a distributed SQL database, having multiple nodes is the norm, is not an exception, like in the case of Postgres, which is a single node database. So we said, how do we do that? And we put a bunch of this logic, some part of this logic into the database side to be able to route connections, but a lot of that into a smart driver, which is library compatible with your standard JDBC or Postgres drivers, but has this connection pooling logic. It can discover the nodes of the cluster. It can establish connections to multiple nodes. So all you're doing is simply connecting to one node, and it can discover all nodes and round robin between them. And it can take care of all the logical connections, and your physical connection goes down and so on. So in effect, the entire application architecture, with all of its hassles and concerns as you're going to production, is transformed from the figure on the left to eliminate the load balancer, eliminate connection pooling as an external thing, and eliminate the bottleneck on the database side to simply make it the thing on the right. So even if you're having one stack per database, like you're having one database cluster per application, this is still pretty easy and manageable, right? And so it's really, really cool to see how this simplifies the application architecture. So all that goodness, and here's a bonus, right? Well, you're probably thinking, all this is great. I have my application actually running on some other database, not Yugabyte DB. And the actual work of moving the application from wherever it's running to Yugabyte DB is a pain. I mean, and let's be honest, right? Most of the developer folks don't want to do that work. It's just a lot of work. So how do you adopt this database? How do we make the adoption of this database easy? Well, that's what this section will cover. We're going to talk about how we are simplifying migrations. Well, the first thing is, being Postgres compatible as Yugabyte DB is, it can leverage, or it works with the plethora of tools that the Postgres ecosystem has to convert the schema and the data for any database to Postgres. So be it Oracle or MySQL or SQL Server, DB2, whatever it is, if it can be moved to Postgres, it can be moved to Yugabyte DB with relative ease, with the same level of effort, right? So to make this even simpler than just figuring out which, there's still some differences between Yugabyte DB and Postgres, fundamentally being Yugabyte DB being distributed and Postgres being a single node, right? But it reuses the upper half of Postgres, so there's a lot of similarity in the schema. So we released this product pretty recently, Yugabyte DB Voyager, specifically aimed at simplifying migrations. Well, what does Voyager do? Well, Voyager reuses the fantastic ecosystem of migration that Postgres has, but makes migrations simple and repeatable, right? Its goal is to get you from any database to Yugabyte DB And it handles this migration in a structured process. It gives you here's phase 1, phase 2, phase 3, and so on. And we're building into it the entire life cycle, all the way from large-scale assessment, all the way down to how do you do live updates and cut over and all of that stuff. And the best part, well, it's completely open source under Apache 2.0 license and completely free, no restrictions. So have at it. Okay, the other cool thing about Voyager is that it actually has built into it, ability to pause and resume, so the resilience, the auto sizing and scaling and observability of the migration process, all of that stuff. So making the migration product itself cloud native. So the aim of Voyager is to get you from a traditional database to a cloud native deployment of Yugabyte DB. So if you're making that transition, this is going to make your life a lot simpler. All right, let's look at how Voyager works, right? So even before we get into the details here, there's one very interesting aspect about Voyager. You can run multiple instances of Voyager to complete these different steps. You don't need to stick to one service or one instance running on a single node. You can do these different steps at different locations and still get the whole migration to work. So giving you enormous amounts of flexibility. If you're moving a database that's sitting on-prem versus something in some other cloud in your own EC2 machine or what have you, it makes all of those much more flexible and easy to accomplish. Okay, so with that, let's jump right in. So we're going to cover just 3 stages of migration here. And note that we're adding a couple of more stages, and I'll talk about it right at the end of these 3 stages. First stage is assessment. You want to know how complex is my source database to move. Let's say you have Oracle. So today Voyager supports Oracle, Postgres, and MySQL. Well, Postgres obviously isn't going to be too hard given Yugabyte DB's compatibility, but it actually can go look at Oracle or MySQL and tell you, okay, this is really how difficult it should be to move this database. Like as in it's very hard, very easy, or somewhere in the middle. And what are the places you'll need manual effort, and you want to go verify that, and so on and so forth. So you can do that by just downloading, installing Voyager, and running analyze schema on your source database and say, how hard is the schema to convert to Yugabyte DB? And it's going to give you a score to do that. Okay, you've analyzed your schema, you've assessed it, you think it's reasonable. Now you want to begin, right? You can actually do the export, modify, migrate. So you can export and import the schema first. And if you export the schema and there are certain sections that you need to pay attention to, like maybe there's a stored procedure conversion that needs your special attention, or maybe there are some features in Oracle that you're using that don't have direct equivalents in PostgreSQL, well, it's going to point those out to you and say, go make those changes and apply those changes, and and come back and we can complete the migration. So once you have converted your schema, you can simply import it into the Yugabyte DB cluster. And you can import similarly the data from the source cluster into your Yugabyte DB cluster. And so now you have both your schema and your data at the end of this step moved from the source database, whatever it is, to Yugabyte DB. And it's the same set of steps irrespective of the source. All right, the third step is to finalize. So you can verify that you've moved all your objects and data, you can run your test queries, and you can cut over your application to Yugabyte DB, right? Now, in these, a couple of steps, a couple of things that we're working on that are pretty interesting, right? So this is how the diagram starts to look. We support a number of flavors of PostgreSQL, Oracle, and MySQL, including a number of the cloud services to make life simpler. But one of the cool features that's super heavily asked for and that's coming soon is the ability to do live updates, which is, let's say you have your Oracle sitting somewhere and you just make a couple of updates to it after you started your migration. Well, the live update feature through Voyager will actually pull those updates and apply it to your target cluster. And you don't even need to know. You just need to set up the live migration pipe and it'll do that. And similarly, you can set up a fail forward capability. You can go and put another Oracle in front of Yugabyte DB and use Voyager to migrate from Yugabyte DB CDC to the fail forward Oracle to keep another system. Once you cut over to Yugabyte DB, if you want the fail safe of actually falling back to Oracle if you ever need, you can build that too with Yugabyte Yugabyte DB Voyager. It simplifies all of that stuff. So it makes the repeatable, the repeated steps for which you had to do a lot of research, pick the tooling, make sure it's carefully orchestrated and works. All of that, it really, really simplifies things. Okay, so to recap, the keynote is about E cubed, embrace, extend, and evolve. And it's really about embracing, extending, and evolving PostgreSQL to make it work in a distributed SQL manner for cloud native applications. Hope you enjoyed that keynote, but don't go away. There are a number of really, really cool and informative DSS sessions. You should definitely check these out. Here's just a few of them, right? The next session coming up is the lessons from Tokopedia on what did they learn about distributed SQL. Tokopedia is a part of is like a pretty big Indonesian company. They're a part of Tokopedia and Gojek. They merged, and so that's a really, really cool session. Do attend it. There's another one. We talked a lot about simplifying applications, and one of the big themes of this entire keynote was how can we simplify application architecture or make it easy for developers or so on. So this session is also, if you're interested in that, do go attend it. It's about improving a developer's life with distributed SQL. There is a technical deep dive in using Yugabyte DB APIs. So, pretty informative if you want to automate stuff. API-based and automated is one of the cornerstones of cloud native. I mean, we didn't really talk about it in this talk, but, nevertheless, it is an important aspect. And so do attend that. In this other session, Frank Patchard, our developer advocate, talks about distributed loose index scan. So do check that out. It's really cool optimizations for distributed SQL when the data is really distributed. And finally, there's a deep dive on Yugabyte DB's change data capture. Again, note that this is a distributed change data capture. So you can have many nodes pushing data out, and you can consume them, and you can do a variety of interesting things with them downstream, right? So do check these out. Once again, this session is primarily meant to be informative, and above all, don't forget to have fun, and do drop a note, say hello. Thank you, folks.